Have you ever wondered how we could predict the strength of a brand new metal alloy before it's even made? Well, today, we're pulling back the curtain on the mathematical secrets that literally let computers see into the future of materials. So let's dive right in.
Okay, think about this for a second. How do we take something you can actually hold in your hand, like the intricate structure of a crystal, and translate it into the language of machines? How do you possibly convert the messy physical world into a clean, elegant mathematical equation? That is the exact puzzle we're going to solve today. You see, for centuries, making new materials has been a super slow grind of trial and error. You make it, you break it, you start all over again. But machine learning is completely changing the game. It's building this predictive bridge, letting us know how strong a material is going to be before a single atom is ever forged. And this is the magic formula. At its heart, it's actually pretty simple. X is our input, think of it as the recipe for our material. Y is what we want to predict, like its strength. The function f is our model, and theta, well, theta is the secret sauce, the little tuning knobs that make the whole thing work. Our entire goal here is to find the perfect theta that gives us the most accurate predictions possible. So, where do we even begin? Well, the very first step is to translate our physical stuff into a language the computer actually speaks, the language of numbers and, you guessed it, linear algebra.
Imagine for a second that we're creating a profile for our material, almost like a dating profile. We list out all its key features, carbon content, grain size, how it was heat treated, as just a string of numbers. We call this a feature vector. It's kind of like giving our material a unique GPS coordinate in this huge mathematical world, so the computer knows exactly what it's dealing with. But of course, we're not just looking at one material. We're looking at thousands. So what do? We stack all those individual feature vectors together, one on top of the other, creating this massive grid of data we call a matrix. Now, each row is a different material, and each column is one of its properties. This is how we give the algorithm a total bird's-eye view of the entire material's landscape.
Okay, so now we've got our data all neatly organized in a matrix. But here's the thing. Raw data is noisy. It's messy. So how do we find the really meaningful patterns, the signal, that's hidden inside all of that static?
In the real world, no two materials are ever exactly alike, even if they're made the same way. So we use two really important tools here. First, the mean tells us the average value of a property, like strength, and then the variance tells us how much that property tends to spread out or vary from that average. It's like finding the bullseye on a target and then seeing how scattered all the shots are around it.
Now get ready for a slightly mind-bending but incredibly powerful concept, the eigenvalue problem. Just picture a strong gust of wind blowing across a field of arrows. Most of those arrows are going to get spun around and point in totally new directions. But a few special arrows, our eigenvectors, they hold their course. They refuse to change direction. They only get pushed forward or backward. These represent the stable, unshakable directions in our data.
And check this out. Here's what that looks like. On the left, we have our arrows just sitting there. Then boom, a transformation hits them like a whirlwind. Most are sent flying in totally new directions. But do you see that one V? That's our eigenvector. It's unshakable. It only stretches out. In materials, this might represent some fundamental truth, like how adding more carbon always increases hardness along one specific axis. That's what we're looking for, these fundamental, stable relationships.
So what's the point of all this? Well, we use it to cut through all that noise. An algorithm called PCA, or Principal Component Analysis, looks at how all of our materials' properties change together. That's the covariance. And then it finds the eigenvector that points to the biggest, most important pattern in all that data. This is literally how we find the hidden signals that really, truly matter.
All right, we've translated our data, and we found the key patterns. Now let's get to the most exciting part. How does a machine actually learn? How does it get better and better over time?
Well, to get better, our model first needs to know just how wrong it is. It's simple. We compare its predictions to the real-world results, and the difference between them is our error. The loss function is just a fancy name for adding up all those errors into a single score. The higher that score, the more our model has to learn. So that frames our challenge perfectly, right? We have this single number that tells us exactly how bad our model is. So how do we systematically, step by step, shrink this error all the way down to zero?
The secret weapon is something called the gradient.
The best way to think of it is like a compass, but this compass doesn't point north, it always points in the direction where the error is getting worse. At any given moment, it shows us the direction of more wrong.
So think about it. If our compass is always pointing uphill to where things are more wrong, what do? It's easy. We go the other way. We take a step downhill. This whole process is called gradient descent. We just take a small step away from the direction of more error, and then we do it again and again and again. With each tiny step, our model gets a little bit smarter, our error gets a little bit smaller, until we're at the very bottom of the valley, the point of minimum error. This, right here, is how a machine learns.
So let's put all the pieces together. Let's zoom out and look at the complete pipeline, from a chunk of physical alloy all the way to an optimized, super accurate prediction. So here it is, the full picture. We take our raw, real-world data and we turn it into a matrix. We use our model to make a prediction, we measure how wrong it is using the loss function, and then we use gradient descent to get a little bit better. It's this beautiful, continuous loop, from the real world to a perfect prediction, and back again. And really, this is what it all boils down to. By mapping that messy, complicated metallurgical reality into these pristine mathematical structures, vectors, matrices, and gradients, machine learning transforms the old, slow method of trial and error into calculated, deterministic prediction. So I'll leave you with this big question. For basically all of human history, we've been limited by the slow, grinding pace of physical experimentation. But now, we have the tools to explore this infinite world of materials at the speed of thought. So what incredible, world-changing discoveries are just waiting out there for us, now that trial and error is no longer our only tool?